For today's video, you will need your in-class 6 notes from your Standard 2 notes packet. We will be talking about angle addition, which is a postulate, and then angle bisector, which is a definition, and then linear pair, which has both a definition and a theorem. So, as we get started, we are going to get moving by thinking about the measurements of some angles. So, as we look at this first picture, they are asking us to find the measure of angle ABC. That is the rotation that would take us all the way through this larger angle in the picture. So if we start traveling, that part of the angle is 65 degrees, this part of the angle is 35 degrees, so the measure of angle ABC would be 100 degrees total all the way from one side of that angle to the other. If we look at example B, the situation is a little bit different. We've been given the measure of angle ABC as 110 degrees. So from A through B to C, they're giving us this larger angles measure as 110 degrees total. And then the goal is to find the measure of angle DBC. So that would be this smaller angle that doesn't have a measurement marked. So if we think about this total 110, if we were to remove or cover up that 70 degree angle, angle ABD, what would be left would be this angle here that we're looking for. So 110 with that 70 degree angle removed is going to give us a measurement for angle DBC of 40 degrees. Last but not least, in example C here for the intro, they're telling us that angle ABC, so again this full angle, has been divided in half. So this ray BD is dividing that angle exactly in half. Which means if this rotation here for angle DBC is 50 degrees, then this one for angle ABD would need to be the same. Using that idea, measure of angle ABD is exactly what we just tracked down. That would be equal to 50 degrees, so that that angle would be divided exactly in half. So these intro ideas actually show us a couple of the different types of problems we're going to be working through for our in-class 6. The first reason that we will see for Standard 2 is going to be angle addition postulate, very similar to segment addition postulate from our previous standard. And so we are going to think about that as being parts of an angle that can be added together to find the measure of the whole angle. So our general equations are going to be set up as addition problems, very similar to segment addition. We're actually going to look at example A and write a general equation for example A. So if we're thinking about the parts of this angle, this top portion that's 65 degrees could be called the measure of angle ABD. The bottom portion would add on to that the measure of angle DBC, and together those two measurements we added to make the measure of the whole entire angle ABC. So you'll notice we need these little m's in front because we're writing an equation that uses numerical values, not just pictures. So the measure of the two smaller parts of the angle add together to be the measure of the entire angle. We could show our work. The measure of angle ABD was that 65, the measure of angle DBC was 35, and together those make the measure of angle ABC. And so we found earlier and have now confirmed with a little bit more formal work that 100 degrees is the measure of angle ABC. Example B up at the top is also the same kind of idea. We would have angle addition postulate as our reason for the work that we did here, except that the way that we did it was actually in terms of subtraction. So we need to be a little bit careful that we don't accidentally write a subtraction equation for our general equation. We want it to look like addition because our reason is angle addition postulate, not subtraction. So if we set that one up the same way, I think we can actually use the same exact general equation because these letters are all in the same location that they were for example A. So we've got the measure of angle ABD again, that's that top section, plus the measure of angle DBC, that's that bottom section that I highlighted in that orange color that was missing. And together those will add to be the measure of angle ABC, the whole angle. Substituting this time, we'll have a 70 degrees for the measure of angle ABD. We do not know the measure of angle DBC, so that will stay. But we do have the measure of angle ABC, the whole entire angle, as 110. And so that is where the subtraction comes in, the work to solve, which gives us the measure of angle DBC equal to 40 degrees like we had previously. Example C is different. We did not use angle addition postulate for example C. We used this description right here that the angle was divided in half. Another way of saying that that is happening is to use the phrase angle bisector. So this is a new vocabulary word for us, which is why you're seeing definition there as part of this new reason. So now we're up to 2 reasons for standard 2, angle addition postulate and definition of angle bisector. So first and foremost, let's talk about the definition. An angle bisector is going to be a ray, like it is in this diagram, or it could be a line if it kept extending out in this direction, that's going to be in the interior of an angle, so it's inside this angle. And then what that ray or line does, if it's an angle bisector, is that it divides that angle into 2 equal angles. Another way to think about that is that it's a ray that cuts an angle in half. Okay? So when we see that phrase angle bisector, that's what we need to be thinking. A ray that divides an angle into 2 equal parts, or a ray that cuts an angle in half. So for example C, up at the top, we had information about the measure of angle DBC, this part that was labeled 50 degrees. So the measure of angle DBC is going to be in our general equation. And we were asked to find the measure of angle ABD. Well, that's just the other part of that angle. So those are going to be equal to each other, thanks to the definition of angle bisector. The measure of angle DBC was 50, so we plug that in. We don't know or didn't know the measure of angle ABD, so that stays put. And then we land on 50 degrees as the measure of angle ABD. All right, that is 2 of the 3 pieces of information that we said we were going to talk about today. Angle addition, which is a postulate, if we turn it into a reason. Angle bisector, which is a definition. And then we have the idea of a linear pair, which is going to have both a definition and a theorem. So we'll see which one of those we'll use when we're actually solving problems once we fill in this bottom section. Okay, first we need to talk about the definition of a linear pair because that's how we're going to know when we're dealing with a linear pair theorem problem. So a linear pair is going to be 2 angles that are what we call adjacent. We'll explain what that means in a second. And they form a straight line. So adjacent is what's happening right here. This ray, HJ, is shared by 2 different angles. This angle to the left, angle GHJ, and then this angle to the right, angle JHI. So because they share that ray in common, and that's the vertex of both of those angles, we can call those 2 angles adjacent. Then the other sides of those angles, so ray HG and ray HI, are what we call opposite rays, which means that they form this straight line that we talked about in the definition of the linear pair. And so what happens if that's the case is that we have some very specific information about what these two angles add up to be. Some of you may have learned about what's called a straight angle in the past. So this part of the diagram is a straight angle. Straight angles always have a measure of 180 degrees. And so the linear pair theorem says that these two angles that we just talked about that form a linear pair must also add up to be exactly 180 degrees because they form that straight angle together. So if we're using this figure that we have over here at the left and they give us the measure of angle JHI as 50, I'm going to trace from J to H to I, and right there in that corner, that's going to be the 50-degree angle they're talking about. They would like us to find the measure of angle GHJ. So angle GHJ is the other part of that linear pair. So our general equation is going to take those two angles, the measure of angle GHJ and the measure of angle JHI, and add them together. The total is always 180 degrees when we have a linear pair. So we'll substitute in our values. We don't know the measure of angle GHJ, so that will stay as is. But we do know the measure of angle JHI is 50. And so then with a quick subtraction, we'll be able to say that the measure of angle GHJ is equal to 130 degrees. And this linear pair theorem would be the reason that we would give to go along with that solution. The definition of linear pair is just what we're looking for so that we're able to use the linear pair theorem to actually solve the problems. All right, go ahead and flip the page and meet me back here to get some examples taken care of. All right, welcome back. We are on the back side of in class 6 where we have 5 different examples that are going to use these 3 new reasons that we've learned about today. So for example 1, let's make sure our picture is all set up with everything that we're given in the instructions. The measure of angle ABC. So the measure of angle ABC, that's going to be this total angle, is equal to 128 degrees. I don't see that on the diagram, so I'm going to draw a big arc, and then connected to that big arc, I'm going to label 128 degrees so that my brain doesn't accidentally think it's one part of the angle, but I know it's that whole thing. The measure of angle ABD, so from A to B to D, is already labeled as 6x plus 11, so that's taken care of. And the measure of angle DBC, so this bottom part of the angle, is already labeled as 6x plus 9, so that's taken care of. Our goal is to find x. So when I look at this, I don't see a linear pair because there's not a straight line. I don't hear angle bisector anywhere. So this is going to be an angle addition postulate problem. And that's going to work out well because I have in my picture 2 smaller angles, the measure of angle ABD plus the measure of angle DBC, which can combine together to give me the total angle, which would be the measure of angle ABC. So if I start to substitute, I use that 6x plus 11 angle first, then the 6x plus 9 angle, and then the total angle is that 128 degrees that I was given at the beginning of the problem. Combining some like terms will give me 12x plus 20 on that side of the equation. Subtract that 20 and we get 108, and then 108 divided by 12 will be 9. Do a quick double check. My goal was to find x. I found x, so the fact that that's sitting in that answer blank is just fine. We're done with that problem. Angle addition postulate. Moving to example 2, Kn is the bisector of angle LKM. So let's look at that carefully. Ray Kn is right here, and they're telling us that that's the bisector of an angle. and the angle specifically is angle LKM. So this is going to be a definition of angle bisector problem because we have a bisector of an angle. So depending on what they ask us to do, we might have to write our equation in one of two ways. Angle bisectors are kind of like midpoints from standard 1, and they can be used in different ways. So our goal is to figure out the measure of angle MKN. MKN. So this is our goal. If the measure of angle LKN is 2x plus 16, so that's taken care of. And the measure of angle LKM, ooh, that's the whole angle, is 6x plus 10. So if we're going to compare the two pieces that we're given, we have a situation where we're given part of the angle and then the whole entire angle. So when this happens, we want to show the relationship that this angle bisector cuts this larger angle in half. So the measure of that smaller angle, which in this case is the measure of angle LKN, is equal to half the measure of the entire angle, which in this case is the measure of angle LKM. Be careful with those letters. So if we substitute in, that smaller angle was 2x plus 16. That smaller angle is half of the whole angle, which was 6x plus 10. And since both of these are easy to do a half of, I'm just going to distribute. Half of 6x is 3x, half of 10 is 5, and so then that gives me an equation that I can pretty easily solve for x. Subtracting 2x, subtracting 5, we're going to end up with 11 equal to x. Now I need to double check. This asks me to find the measure of an angle, and I don't have an angle yet, I just have x. So to finish this one out, let's go back and investigate where the measure of angle MKN is directing us. That's this piece over here, which we actually don't know anything about. But if we remember what an angle bisector does, it divides this angle in half, which means whatever this angle is, the other half needs to match. They're equal. So I can find the angle that I need by focusing on this 2x plus 16. The measure of angle MKN is going to equal 2x plus 16. So we take that 11, we plug it in. The measure of angle MKN would be 22 plus 16. So it looks like our final answer for the measurement of that angle MKN would be 38 degrees. So a little bit more effort at the end because they didn't just want us to find x, they also wanted us to find the value of a particular angle. Alright, let's see what's going to happen in example 3 here. So for example 3, we've got the measure of angle PAR, that's already labeled to match what they gave us. The measure of angle RAT, already labeled to match what they give us. And then last but not least, the measure of angle PAT. Alright, that's that entire angle there, which is a little bit tricky to label when there's so much going on, but that whole thing would be 30x squared plus 22. I don't see a straight line, so this is not a linear pair theorem problem. I don't hear or read anything about a bisector, so this is not a definition of angle bisector. So this is going to be a second angle addition postulate example. And so when we write our general equation, we're going to use the measure of the two smaller angles added together. And when those are combined, they equal the measure of that larger outside angle. So if we substitute in our values, the measure of angle PAR was 13x squared plus 5. We're going to add on to that the measure of angle RAT, 20x squared plus 5. And then together they make the measure of the whole angle, 30x squared plus 22. This one does have some algebra in it, so if we combine some like terms, we're going to have 33x squared plus 10 equal to 30x squared plus 22. And since I only see x squareds and no x to the first, I'm going to move all the x squareds to one side of the equation, so there'll be 3x squareds. I'm going to move the numbers to the other side of the equation, so subtract 10 gives me 12. Simplify to figure out what x squared is equal to, and then I can solve this one with square roots, which gives me both positive and negative 2. Doing a quick check, my goal is to find x, so as long as both of these answers work, I'm going to have two answers to this problem. So if I think about plugging in positive 2, squaring would be positive. Everything seems to be checking out there if I were to evaluate all of those. And I don't think anything different is going to happen if I plug in negative 2, because all of the x's are going to be squared, so those angle values will still all turn out to be positive. So x is going to equal either positive or negative 2 for this problem. Two answers. All right, two more examples. So for example 4, I noticed something right away. Ray AN bisects. So that means this is going to be a second definition of angle bisector problem. Ray AN bisects angle LAD. So this side of the angle is going to match that side of the angle. And thinking about what's already labeled here, I'm guessing that's what I'm going to focus on for my general equation. So the measure of angle LAN is going to equal the measure of angle NAD, which will allow me to set 2x plus 93 equal to x plus 84. Subtract x from both sides, subtract 93 from both sides, and that's a little interesting because if we do 84 minus 93, we're going to get a negative value for x. But if you go back and you double check, 2 times negative 9 would be negative 18. When we add 93, that's still a positive measure for that angle. Negative 9 plus 84, still a positive measure for that angle. Since x is the goal, that's it. X equals negative 9, and we're done. Okay, one last example. Example number 5, and when I'm looking at this diagram, I see something different than all of the others. There's that nice straight line. So this last problem is going to be our example of linear pair theorem. Those two smaller angles, so the measure of angle FAS for the one on the left side, adds together with the measure of angle SAT on the right side to form 180 degrees exactly, thanks to that nice straight line and those two adjacent angles that share that side in common. So if I substitute, I'm going to take that 6x plus 8 from the angle on the left, the 4x plus 27 from the angle on the right, add those together to be equal to 180. Combining like terms is going to give me 10x plus 35 equal to 180, and then we can finish out our solving for x and do a quick double check to see if that's the goal or if we've got more to do. So x is going to be 14.5. This is asking me to find the measure of angle SAT, so I am not done. I'm going to come over here to the measure of angle SAT, and I'm going to do 4 times 14.5 plus 27 to finish that out. Grab a calculator real quick, just so that I don't accidentally make any mistakes with my arithmetic. 4 times 14.5 is going to be 58. Add 27 onto that, and we end up with 85 degrees total for the measure of angle SAT. Alright, that's it for today. Bring those back with you to class tomorrow.